Today I'd like to take a little bit of time to just go over a set of notes we did in class about rational and irrational numbers. And as we worked with the Pythagorean theorem and triangles, we've run into different types of numbers. And so two of those types of numbers are rational and irrational numbers. And we want to know what the difference is between those two. When we look at a rational number or an irrational number, what do we mean by those terms? And so I have some notes on the page that I'm going to go through briefly just to try to give you an overview of what the difference between a rational number and an irrational number is. So I've started on my page with changing some fractions into decimals. And there's a couple different types of decimal numbers. The first type, if I take 1/2 and convert it to 0.5, or if I take 3/4 and change it to 0.75, or 3/8 and change it to 0.375. These are all examples of decimals that terminate. They're called terminating decimals because there really is no number after 5. We could put a 0 in there, but that 0 would really be adding nothing. It might be a precision 0 in terms of a measurement if we were using a tool, but for the most part, these decimals simply end. And even if we put a 0 behind the 5, the 0 doesn't add any value to it. So these terminate. So we can take a fraction and convert it into a terminating decimal. And terminate just simply means to end or stop. It's the end point. And so these decimals terminate. They simply end. Other decimal numbers don't end. They repeat over and over again. So if I take 1/9 and convert it to a fraction, it actually comes out to 0.1 repeating, and that 1 continues on and on and on forever. So we really don't have a change. It's just simply 0.1. And one of the ways that you can determine these is by taking the actual fraction and putting it into a calculator, and then you can see the example of if I take 1 divided by 9, which is how you convert any fraction into a decimal. And you can see that endless set of ones repeating, and the calculator just simply runs out of spaces, so it puts in as many ones as it can and stops. And so we note that as 0.111, or we could do a 0.1 with a line over the top, and the line shows that the decimal repeats and keeps going. Same thing with 2/9. If I did 2 divided by 9, see that I get 0.2 repeating. And so again, these decimals, 1/3 comes out to 0.333, and we just continue to get 3's if I put 1/3 in there. And so there are my repeating decimals. They just repeat over and over again, and the way to note them is 0.3 with a line over the top. These are called repeating decimals because they repeat. And really, the reality is you can predict what's next forever. I always know there's going to be another 3 after this one. Even if I go out 100 digits, there's going to be another 3. It just continues to repeat over and over and over again. And so if we look at a few other examples of decimals then to fractions, we should be able to go either way with this. If you can change it from a fraction to a decimal, we should be able to go from a decimal to a fraction. So 0.3, the fraction would be 3/10. Whereas the decimal 0.3 repeating actually is the fraction 3/9, or what we normally say would be 1/3. And so when it repeats, it actually ends up being a slightly different fraction. We can always check them to see how that, we see that we had 1/3 before and it comes out to 0.3 repeating, which is the same as 3/9. Or if I had 0.4, that would be 4/10 or 2/5 as a terminating decimal, but as a repeating decimal, it actually creates the fraction 4/9. And the same is true if I look at 0.5, which is 1/2, or 0.5 repeating, which actually ends up being 5/9. Now this one's an interesting one because if I do 5/9, sometimes people say, well, it's not really repeating because at the end you end up with a 6. But the only reason you end up with a 6 at the end is because the calculator runs out of spaces, and if you have a 5 or greater at the end, you have to round it up. So these other ones never rounded up because they were below 5. So calculator is going to round off or round up in this case to the whatever number is next determines that, and a 5 with 5 or greater you round up. And so that's the only reason this shows up this way on the calculator. And so again, we have this 5/9 as opposed to 5/10 for the repeating decimal. And again, 6/10, which is 3/5 or 0.6 repeating, actually is 6/9 or 2/3. So you see that repeating decimals and terminating decimals both have fractions that represent them. They're just slightly different because of the way they are represented. Now, all these decimals that I've shown on here are actually rational numbers. And the reason that they are all rational numbers is because they can all be written as a ratio of two numbers. They all can be written as exact fractions. So the exact fraction of 0.3 repeating is 1/3. The exact fraction of 0.4 repeating is 4/9. The exact fraction of 0.5 is 1/2. Every one of these has an exact fraction representation for it. And so they are considered to be rational because they can be written as a ratio, 1:3 or 1/3, 4:9. Every one of these has a fraction form. And they can go back and forth from fraction to decimal or decimal to fraction. And so that makes up the set of numbers that we call rational numbers. Even whole numbers are considered rational because you can simply take a whole number or any whole number. Like if I took the number 6 is a rational number because it can be written as 6/1. So the whole number ratio 6:1. So even whole numbers are considered rational. You can always write them as ratios. Now, there's a whole nother set of numbers that are roots or square roots. And some square root numbers are actually rational. For instance, the square root of 1, which is simply 1, can be written as a fraction 1/1. So we have two whole number representations or numbers that are represented as a fraction. Same thing with the square root of 4. It equals 2, so it's 2/1. The square root of 9 is 3, so 3/1. So there's a whole bunch of rational square roots. The square root of 16, the square root of 25, any of the, what we say, perfect square roots that have whole number solutions are also rational numbers. But then we get into a whole bunch of other numbers that we have a little problem with, like the square root of 2. And I've approximated the answer to the square root of 2 as 1.414, but if I actually put in the square root of 2 in my calculator, you can see that I get 1.414213562. And the problem is I don't really know what's next. Some people think, well, it just terminates, it ends right here. But I don't know that either. And even if I got a bigger calculator, it might go out a few more digits. At some point, it looks like it's going to stop, but I don't know. And because I don't know, I have to just basically give an approximate answer. So I say 1.414. If I wanted to go further, I could carry it out further digits, but most of the time, when we look at something like the square root of 2, we just simply approximate it out to 1 or 2 numbers after the decimal point, depending upon how accurate we want to be. But again, I don't know exactly what it is, and in fact, if I wanted to try to turn it into a fraction, I might use the fraction 7/5, but even the fraction 7/5 is an approximation because if I go the other way, you can see that the best I get is 1.4. And so the square root of 2 is an approximation solution. Same thing with the square root of 3. It's about 1.732, and again, if I put it into my calculator, you can see that it's got a whole bunch of other numbers, but my calculator eventually runs out of space. Sometimes people look at this one and say, well, it looks like it's going to go 0808, but I don't know if that 8 is a result of that being an 8 or if the number after it made it round up. It could have been a 7 and could have been rounded up to an 8. And so because I don't have a powerful enough computer, basically, in this calculator, I don't know. And the reality is most of these numbers have been calculated out much further with much more powerful computers, and we've seen that the numbers don't repeat and they don't terminate. And if you remember from the earlier part, we were looking at repeating and terminating decimals as rational numbers. So if they don't repeat or terminate, they don't do something over and over again that I can predict, or if they don't just end, then I've got a whole different set of numbers, like the square root of 5. Again, I don't know what it exactly is, so I approximate it as 2.236, and it's about 2 and 24/100ths as a fraction. And this set of numbers now, these kinds of numbers like the square root of 2, the square root of 3, the square root of 5, the square root of 6, the square root of 7, the square root of 8, all the roots in between these don't have exact values. And we can't write them as exact fractions, so we say that they are irrational. Ir meaning not, so they're not rational. There is no fraction that can be written to represent these numbers exactly. We don't have an exact fraction value. It's like the number pi. A lot of times people use the number pi as a representation of what it means for numbers to be irrational. Most of the time we approximate pi as 3.14. Some people have memorized it out much further than that, but eventually you just get to the point where you don't know what the next digit is. Even with the most powerful computers, pi has been calculated out to many, many digits, but the ability to predict beyond where those go is unknown. And so therefore we have these irrational numbers because we don't know what's next. And at some point we can't predict what's next. We might have a list that we could read off of, but the number itself does not give us any way to predict. So numbers that cannot be written as an exact fraction or ratio or decimal that repeats or terminates, these are the numbers we call irrational numbers. These are our irrational number set, and there's lots of them. And when we're dealing with triangles, right triangles, and using lots of square root solutions, we have lots of irrational number answers. The square root of 7 is irrational because I can't write it as a ratio of two numbers. 0.27 repeating, on the other hand, is rational because I can write it as 3/11ths. And so rational numbers include fractions and all terminating and repeating decimals and the perfect square roots, because an irrational number is any number like the square root of 2 or pi that can only be approximated and cannot be written as a fraction that exactly represents the number. And so now we have this whole set of numbers, rational and irrational numbers, that we use all the time. These irrational numbers are actually distances, oftentimes diagonal distances across squares, which we have used many times in our exploration of the Pythagorean theorem. So that gives you a sort of brief overview and some notes we took in class, and you can go back through this or slow it down or pause it if you want to write down more of what the notes say to help you remember and understand what it means for numbers to be either rational or irrational.